Pluto is a distant and bewildering planet that was once a part of our nearby planetary system's family. However, progressing disturbing announcements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a staggering revelation. They suggest that this freezing world is on a potential brief trajectory with Neptune. However, how could this happen, and what might be the results of such an enormous event? Are we witnessing an approaching immense collision, or is there something different about this oncoming cosmic event? Join us as we explore the potential outcomes of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf planet partly due to its exceptional orbit, remains a subject of interest and study in the cosmic community. As demonstrated by recent forecasts from leading specialists, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential hazardous encounter between these two planets that could represent a tremendous risk to Earth. But how is such an event even possible? Pluto's excursion around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning since its discovery in 1930, it hasn't even completed one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its extraordinarily bent shape, deviating significantly from the almost round orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, determined at 17 degrees to the ecliptic plane. The way Pluto follows its path is much steeper compared to the other planets. This inclination and irregularity add layers of complexity to its orbital pattern. Possibly one of the most captivating parts of Pluto's orbit is its convergence with Neptune's orbit. For nearly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging what we might expect from their positions in the solar system. This leads to the common question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to sort out its strange orbit. Unlike other planets whose orbits lie fairly close to the ecliptic plane, Pluto's path stood out with its steep inclination and irregular shape. The mystery grew with the realization that Pluto's orbit indeed crosses Neptune's. The complexity of Pluto's orbit amidst these intricacies is proof of the complexities of space mechanics. The three-body problem in space involves sorting out how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like attempting to predict where they will go based on where they start and how they pull on each other. For Pluto's situation, this issue shows how its orbit, Neptune's path, and the Sun's gravity all work together in a complex way. The terms alpha libration and scope libration, along with the VSK swaying, are important to this enigma. According to astrophysicists, what's keeping all planets in their orbits is a phenomenon called alpha libration with respect to Pluto and Neptune. This term essentially means that when Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is crucial in keeping their orbits from impacting. Extension libration, on the other hand, refers to the upward movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's positioned well above their orbital plane, offering an additional layer of protection from potential impacts. Another significant factor in this situation is the VSK swaying, named after three researchers, Bond, Zippel, Leo, and Kai, who studied how things move in space. It's about how three celestial objects like Pluto, Neptune, and the Sun pull on one another with their gravity. This pulling influences how they move. In Pluto's case, VSK helps us understand why its orbit around the Sun is so unusual. Despite Pluto's orbit seeming turbulent, this swaying helps keep it moving smoothly from now onward, indefinitely. The VSK sway shows that even though things in space may appear wild and unpredictable, some patterns and rules keep everything together. These factors help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or lose its course. Mathematical simulations in the late 1980s revealed that despite these stabilizing factors, Pluto's orbit is still relatively chaotic, with minor variations in starting conditions leading to massive differences over millions of years. However, These unusual properties of Pluto's orbit have been found to maintain stability over exceptionally long timescales, effectively keeping the chaos in check. Recent computer models have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's orbit stable. However, Neptune isn't the only one contributing. Jupiter's gravity also plays a major role in defending Pluto's orbit, and Saturn contributes significantly as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable orbit for a long time, even billions of years. It seems that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These phenomena are critical when it comes to the universe, as they maintain the order and consistency of celestial bodies' movements. Without these forces, the solar system, as we know it, would be a place of much greater disorder and unpredictability. Bodies like Pluto might collide with others or be ejected from their stable orbits, causing a domino effect on other celestial bodies. For Pluto particularly, with discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial. This gives us a clearer picture of the dynamics of our solar system. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of stability through the intricate exchange of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the strange nature of celestial bodies, and Pluto's orbit is a perfect example of this oddity. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is strikingly illustrated in the case of Pluto. This means that even slight changes in the dwarf planet's position or speed can significantly alter its long-term trajectory. In the vastness of our solar system, Pluto occupies a unique place that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant revelations about its structure and behavior. One of the most intriguing aspects of Pluto is its surface, which is a complex tapestry of ice, rock, and other compounds. The New Horizons mission, which flew by Pluto in July 2015, provided striking data about this distant world. The surface of Pluto is characterized by vast fields, towering mountains, and deep valleys. One of the most remarkable features is the Sputnik planum, a colossal heart-shaped plain primarily composed of nitrogen ice. This area showcases a diverse array of landforms, including large ice shelves and what appear to be flowing glaciers. The presence of these features suggests that Pluto may still be geologically active despite its great distance from the Sun and low temperatures. Another captivating aspect of Pluto is its atmosphere, primarily made up of nitrogen with traces of methane and carbon monoxide. Pluto's atmosphere is thin but shows intriguing seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior is a reflection of the complex relationship between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that both bodies are in a mutual orbit around a point in space that lies between them, rather than Pluto simply revolving around Charon. This unique relationship contributes to the complex gravitational dynamics in the region, affecting the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to various other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, giving scientists a glimpse into its formation. Pluto's orbital characteristics may provide insights into the development patterns of these distant objects, suggesting that interactions with larger planets may have played a significant role in shaping their current orbits. One of the key implications of understanding Pluto's orbital dynamics is the potential impact on our understanding of the solar system's evolution. Gravitational interactions from neighboring giant planets like Jupiter and Neptune can alter the trajectories of smaller bodies, including those in the Kuiper Belt. Such interactions can lead to shifts in orbits, possibly resulting in collisions or ejections from the solar system. As scientists continue to explore the details of these interactions, they may uncover broader patterns that govern the behavior of celestial bodies throughout the universe. The study of Pluto also raises philosophical questions about classification in astronomy. The decision to reclassify Pluto as a dwarf planet in 2006 was controversial, sparking discussions about what it means to be a planet. In conclusion, Pluto's orbital relationship with Neptune and its position in the solar system serve as powerful reminders of the complexity of our universe. The subtle and intricate forces that keep Pluto and other celestial bodies in their orbits are indicative of a far-reaching system of balance and stability. While the possibility of a catastrophic collision between Pluto and Neptune seems unlikely due to the complex gravitational interactions, Pluto's orbit and the study of its behavior continue to reveal valuable insights into the mechanics of space. Understanding this distant world will help refine our knowledge of the solar system and the larger universe that it is a part of. In addition to its fascinating orbital mechanics, Pluto's role in the solar system structure highlights its importance in understanding the broader dynamics of distant celestial bodies. As one of the most well-known members of the Kuiper Belt, Pluto holds a unique position that makes it an excellent object for studying the outer solar system's evolution. The Kuiper Belt itself, where Pluto resides, is a vast region filled with small icy bodies and dwarf planets. It is often compared to the asteroid belt between Mars and Jupiter, though it is much more expansive and populated with objects that have remained largely unchanged since the early formation of the solar system. The Kuiper Belt is thought to be the source of many comets that occasionally venture into the inner solar system. These icy bodies are relics from the early solar system, offering clues about the conditions that existed during its formation. Pluto, as one of the largest and most studied objects in the Kuiper Belt, serves as a benchmark for understanding this distant and relatively uncharted region. Its orbit, which crosses Neptune's path, also raises questions about the gravitational influences at play in this far-reaching area of space. One of the most significant discoveries in recent years regarding Pluto came with the New Horizons mission. The spacecraft, which passed by Pluto in July 2015, provided humanity with the first close-up images of the dwarf planet. These images revealed an astonishingly complex world, far more diverse and geologically active than previously imagined. The presence of large, expansive plains, towering mountains made of water ice, and deep valleys suggests that Pluto's internal structure may be more dynamic than expected, even in its remote location far from the Sun. New Horizons also revealed that Pluto's atmosphere is not as static as once thought. Despite the planet's cold temperatures, the atmosphere of Pluto undergoes seasonal changes due to its elongated orbit. As Pluto moves closer to the Sun, the thin atmosphere expands and thickens, while it contracts as it moves farther away. This interaction between the atmosphere and surface materials, such as nitrogen and methane, causes surface features to evolve over time. The observed behavior of these gases provides vital insight into how planets and moons far from the Sun manage to retain atmospheres and maintain surface activity despite extreme distances. Furthermore, Pluto's moons, particularly Charon, play a significant role in its gravitational dynamics. Charon, which is almost half the size of Pluto, has an unusual relationship with its parent planet. Both Pluto and Charon orbit a common barycenter, a point in space that lies outside of Pluto itself, making this system more of a double dwarf planet system than a planet-moon relationship. The tidal forces between Pluto and Charon are strong enough to cause significant geological features on their surfaces, including vast chasms and mountains, which are thought to have been formed by this constant gravitational interaction. This dynamic relationship also plays into the long-term stability of Pluto's orbit. The tug-of-war between Pluto and Charon can affect the trajectories of other objects in the region, and even small changes in these interactions over millions of years could potentially lead to shifts in the orbits of bodies within the Kuiper Belt. This is one of the reasons why studying Pluto's position and behavior in space is so crucial for understanding the future evolution of the outer solar system. The study of Pluto's orbital mechanics also intersects with our knowledge of larger celestial bodies, such as Neptune. Despite the potential for a collision, as suggested by some scientists, the gravitational interactions between Neptune and Pluto act as a stabilizing force. These interactions keep the two bodies from colliding, even as their orbits come into close proximity over the course of their long, elliptical paths. The gravitational lock between the two objects is an example of how seemingly chaotic systems can maintain stability through complex interactions. Beyond the gravitational relationships, Pluto's surface and atmospheric conditions provide a glimpse into how other distant worlds might behave. Its icy surface and the possibility of subsurface oceans, though still speculative, suggest that even in the coldest regions of our solar system, there may be the conditions necessary for life. While Pluto's distance from the Sun makes it an inhospitable environment for life as we know it, its intriguing features continue to captivate scientists and spark discussions about the potential for life elsewhere in the cosmos. The ongoing study of Pluto and its interaction with Neptune, along with its position in the Kuiper Belt, offers a wealth of information about the solar system's distant reaches. Whether it is the orbital dynamics, the geological features of its surface, or the surprising seasonal variations in its atmosphere, Pluto continues to provide valuable lessons in the complexity of celestial mechanics. Through continued observation and technological advancements, scientists hope to uncover even more about this distant dwarf planet and its place in the cosmic puzzle.